Hi guys, let's start with today's topic. Before we start with today's lecture, there are 2 to 3 key concepts that I meant to cover in the previous lecture. First one is the vector addition. Now, last time we learned what is a vector. It is basically a unit that has a magnitude and a direction. It is like an arrow in the space. So today we are going to learn how to combine them together and do vector addition. Now the first and foremost rule for the vector addition is that both of the vectors should have the same dimension, or they should have the same number of components. Like in this example they have 2 components, so I can combine them together. Okay, so it's basically like saying that I keep all my pants together and shirts together in a wardrobe, and segregate my pants and shirts because my so basically my pants are similar, so in the same fashion, in the same manner, only those vectors I can combine that are of the same dimension. Okay, so that's how you combine them, is basically add the respective components with each other. Now one thing to note in the vector addition is that the order doesn't matter. Like for example, if I compute my v plus w, that would give the same resultant vector as the w plus v, and this is known as the commutative property of the vector addition. Now vector subtraction also follows the same idea, where we subtract their respective components from one another, but this time the order does matter in the vector subtraction. So if I compute my v minus w, and that gives me a vector in a space like that, so my w minus v would give me the vector in a space that is in a completely opposite direction, but it would be of the same magnitude. So it's basically saying that my vectors would be of same magnitude but in a completely different opposite direction. So the order does matter in the vector subtraction. Now one thing to note is that the zero vector is not the same as the number 0. So if I'm saying my that it is a 0 vector, you wouldn't assume it to be the number 0. Now why do I say that? Is because my 0 number is just a scalar that has no direction, but in the 0 vector, it is basically a vector that is living in a vector space. Okay, it is living in a vector world, and that is not the same as the number 0, because it has components. Now in this example there are 2 components of this vector 0, so that's how it's denoted. Now why do I say that my vector 0 is not the same as 0 vector? Because you wouldn't say you can't add a number to a vector exactly. Like if I say that I add a number 5 to an arrow of 2 comma 3, that wouldn't make any sense, right? So that is why I say that the vector 0 is not the same as the number 0. Okay, now let's come towards the graphical representation interpretation of vector addition and vector subtraction. Now let's compute v plus w first. Okay, so here in this example I have already taken my v vector that is represented in my vector space like that. Okay, so first thing that you need to note is that in the vector space you can move your vector anywhere you want, as long as its magnitude and direction is remaining the same. Okay, so I can move my vector, because I can move my vector anywhere I want, because its magnitude and direction is remaining the same right now, because vector is not defined by a starting point, it is only defined by its magnitude and direction. So let's say for the vector addition I'm going to move it to the head of the first vector. Okay, so for me to compute the resultant, what I'm going to do is join the tail of the first vector with the head of the second vector, and that would give me the resultant. It's basically like saying joining the initial and the final position from where you started and where you have ended. So that's how I compute my vector addition. Now here you would realize that you can reconfirm the magnitude of the components as well. For example, here you would see like this is my resultant, so the magnitude of the x component is 3, and here you, if you compute it manually, it is coming off as 3. Now the y component is 5, and when I calculate it manually, it is coming out to be 5. Now for vector subtraction, let's assume I'm going to compute w minus v. So what I do is I take my vector w, and then I added to with the by first of all reversing the direction of V and then adding it to W. So basically what I'm doing is, first of all I'm reversing the direction of V, that would give me this vector, and then adding it. So what I'm going to do is I'm going to first move it towards the head of the first vector and then compute its let's say I compute it with this color. So this would give me the resultant of the vector subtraction. Okay, so here I would realize that my W plus minus V in the similar fashion can be computed as 5 and 1, and it is the magnitude of the x and the y components of the resultant are coming off as same. Now I want to move towards now I want to head over to Marimo to fully grasp what it means to add two vectors. Here first of all I will take the previous example only, where my u vector's x component was 4, so you can actually see and the y component's value was 3. For the second vector, the x component was -1 and the y component was 2. So my resultant is coming off like that, and here you can confirm as well that its x component's magnitude is 3 and y component's magnitude is 5. Now let's assume I take any value, I can change to whatever value I want, and I can compute my resultant vectors. So that's how you can play around. So I think you can come visit this site and play around yourself to make the concepts more intuitive. Here you have scalar multiplication as well, and vector multiplication as well, that you can do it yourself. Okay, now let's head towards the scalar multiplication. It's very easy. It's basically taking a vector and scaling it with some number or weight. In this example I have taken, like, this is my 1, 2 vector, and let's assume the value of c is 2. So it's basically going to double the magnitude, but its direction is going to be the same. We are not doing anything to the direction. Now let's assume if I would have taken -2 instead of 2, so it would have reversed its direction as well. So it would have been this vector but of the opposite direction. Okay, so that is what my scalar multiplication is. Now comes the interesting part, that is the linear combination. Now what it does is, it first of all scales the vectors together and does the vector addition on them. So the two key concepts that you learned up till now, that is vector addition and the scalar multiplication, it takes both of these two together and linearly combine them. So this resultant equation is known as the linear combination of V plus W. So in let's, for example, I have taken one example for you guys. Okay, let's assume my V vector is this of 3 components and my W vector is this. So for me to plot this point, it's basically going to require a 3D space, right? So I would require a 3D space to plot these vectors. So if I have computed the resultant already, so you would realize here that I have 3 components, out of which 2 of them are free variables. Now what it means is it basically can take any value that they want. They are not restricted by any equation or by any constraint, so they can take any value they want, and third of its component is constrained or restricted by some condition. So you would realize here that in this plane or space, I have a linear combination in which 2 of those components can take any value and 1 of them is restricted. So I can say that the degree of freedom is 2, right? So if my degree of freedom is 2 and I am in a 3D space, what is the geometrical object you think is going to be drawn here? I think the example is I think the answer is pretty clear. It's going to be a plane. So for this example, which consists of a vector of 3 components, their linear combination of 2 of those is going to give me a plane in a 3D space. Okay, so that is what the linear combinations are. Now let's head towards the combination of matrices and vectors. Okay, so So previously we studied what AX equals to B means. What AX exactly means, it basically is the linear transformation from Rn to Rm. In the similar fashion, I can interpret the combination of my matrix and the vertices as the row interpretation and column interpretation. For example, I have taken this matrices that consist of the combination of my column vectors. Like these are my column vectors, these are not components, okay? So my A consists of my combination of column vectors, and I have a input vector as well that consists of components of input space. So what would their combination would give me, like what would their multiplication would give me? And first off I'm going to interpret this by column view. I'm going to interpret their column view. So what exactly column view does is, column view says that the AX is the linear combination of the columns of A with the components of X as its weight. Okay, so let's demonstrate it with an example. Okay, so what basically it's saying is कि what I do here is I have a, let's take the geometrical interpretation, कि what it does is कि it takes the my matrices system of a linear equation, and it basically takes the columns and it scales them by their respective weight. For example, here it is X, and for the second vector it is Y. I have taken this system, and in this example what is going to do is it is going to take the column and it is going to scale them by their respective weights, and the combination that I get here is known as the linear combination of columns of A. Now you would realize here why is it known as the linear combination, because first off I'm scaling them and then I'm adding them together. So earlier we studied this is known as the linear combination. So that's basically what is happening here, कि I took these vector, and in this example I know that if I take the value of X as 1 and Y as 2, it would lead me to my resultant vector 0, 3. So I took the first vector as like this and second vector and scaled it by 2, and I can shift my vectors anywhere I want. So it would give me the resultant vector that I wanted, 0, 3. So that is the column picture or the column interpretation of AX equals to B. Okay, now uh, let's head towards the row view. Also you can also view this as like one intuitive example that I can give you is, it's basically you can consider these as the ingredients for a recipe. So let's assume this is my first ingredient as my second ingredient, and what AX basically asks me is what amount of my first ingredient and second ingredient is required for me to make my desired dish. So that's what basically X1 and X2 is doing. It's basically asking how much of this ingredient is actually required for me to make this specific recipe. So that's what column view is. Now let's head towards the row view. So what it basically does uh, is it's basically the another interpretation of the combination of matrices and vectors. So the row view, so in the row view when you are computing AX, so the each row of A, so as the name suggests, what we are going to do is we are going to take each row and we are going to do the dot product of each row with the components of the X input vector. So it's basically giving me the constraints for the system of linear equation. These are the constraints. Now why do I call that a constraint? I would explain it in a bit, but it's basically the combination of a constraint in a system. So it's basically taking rows, it's and doing the dot product with the respective components and giving me the equations for a system for me to solve. Okay, so why did I call that a constraint? So you would realize here कि let me give you one example which would be really, so that it would be easy for you to understand. Okay, so let's assume like this is my system. Okay, this is my matrices system, AX equals to B. So what constraints are basically, let's assume like this is a playground, like this XY variable space is my playground, and I can roam around anywhere I want as long as there are no restrictions on me. So if when there was no A, like there was no matrices A, there were only variables X and Y, I could roam around anywhere. Now let's assume that your PT teacher comes in and instructs you to walk around this path only. Now you are being basically instructed to walk around this path only. So basically they are putting a constraint on you. Now you cannot move here or here, and you can walk around this path only. So it's basically putting a constraint. That's what exactly equation does to a system. It basically constrains your movement. Okay, it basically constrains the movements of the variables. Now let's assume you have another PT teacher, and she orders you to walk around this path. Now you are basically obliged to follow both of the PT teachers PT teachers rules. Okay, so what you are basically going to do, if you have to follow both of their instructions, you are going to find the common point where you can stand. So both of them are like both of their instructions are satisfied, so you are going to find the intersection point or the common point. Now this intersection point or the common point is what we call the solution of a system. What it basically is saying is, this is the point that satisfy both of these equations at the same time. Like this is the only point, in this case this is the only point that satisfy both of these equations simultaneously, and that is why it is known as the row picture, because it's basically focusing on the rows, and basically when the constraints are formed, and then we supposedly find the solution by through their intersection point. Okay, one limitation of a row view is that now if I discuss the limitations of the row view, it is that I cannot imagine geometrical objects for the higher dimension. Now for this example, it was very easy for us to visualize a line in a plane. Okay, so if I move towards the 3D, it would be still easy for me to visualize a plane, right? But as I go into the higher dimension, it would be really hard for me to visualize a hyperplane. So that's when my column vector outshines, because I would just have to visualize a vector in a space. Okay, and it's really easy to do so. So that is why most of the time we prefer column picture over the row picture, because in that we only have to visualize vectors in a space. Okay, yeah. Now what is the difference between the row picture and the column picture? So if I talk about the key difference apart from all the points that we have studied so far, it is that in the row picture lives in the input space, meanwhile the column picture lives in the output space. So let's see how. Because in the row space you would realize that we are playing around with the components of input vector. Okay, so I am playing around with the components of the input vector, and I am drawing the space in accordance with the number of input vectors. So that is why it lives in the input space. But for the column space, you would realize that we are mainly focused on the columns of the column vectors of A and the resultant vector B, and my resultant vector B is what? The output space. Okay, so that is why my column picture lives in the output space, meanwhile my row picture lives in the input space. So that is what my interpretation of Ax equals to B in the form of row picture and column picture was. Now let's head towards the matrix multiplication. Now why I have inculcated this topic, although it's not really taught, is because you would realize your visualization power would increase so much that you would realize that in how many ways you can actually interpret matrix multiplication. In this case, I'm going to discuss two examples that how you can how you can visualize your matrix multiplication as the combination of columns and as the combination of rows as well. So that's what our main agenda of this topic is. Okay, so let's move forward. I have taken again 2 by 2 system because it's easier to solve and visualize. Now here I have taken two matrices A and B, and I have computed the matrix multiplication beforehand. Like I already did it before. Okay, so here I have my C vector. Okay, so first what I'm going to do for the combination of column vector, like from through the column perspective, is first of all I'm going to do the basic multiplication matrix. I'm going to follow a basic matrix multiplication rule, and I stop after the first step. Like this is my first step of the matrix multiplication is right. So I'm going to stop here and I'm going to analyze this matrices. Okay, so what you are going to realize here is, like, this is my column, first column vector of A, and it has been scaled by the component of B. like this is my component B, and it is basically scaling my column of A, and then I'm adding it with the second column of A, which has been scaled by the second component of B. So you can say that my first column of C, which is this, is basically the linear combination of columns of A which have been scaled with the weights of B, right? So you can say that that is how I can interpret my matrices multiplication, is that my columns of the resultant vectors are basically my linear combination of my columns of my first vector, which have been scaled by the columns of the second vector, second matrices, sorry, and you can compute the second column as well in the similar fashion. Okay, so what we studied here is कि it's basically my matrices and the matrices multiplication. My resultant vector is basically the linear combination of columns of first vector which have been scaled by the components of second vector. Okay, now seeing the row perspective, you can see here that my row, which consists of these numbers, is basically the combination of rows of B, like these are my rows of B, right, and they have been scaled by the components of A. So you can say that my you can interpret the resultant vectors as the combination of rows of B which have been scaled by A matrices as well. So you have seen what the resultant vectors through column perspective and through row perspective. Okay, so let's move ahead towards the final example of this lecture, which is this one. Here I have taken one column vector and one row vector. Now I have computed their resultant already. So here you would see that if this is my row, so what it is doing is that all of my rows of C are basically the linear, it's basically been scaled by the components of A. Like let's assume this is A, so it's basically the scalars, like this is my row B, and it has been scaled by the components of A. So these are basically my rows of B which have been scaled by A, and through column perspective you would realize that my columns of A have been scaled by the components of B. So it's basically the combination of columns of A which have been scaled by their respective weights. So you would realize here in this lecture, what you realized in this lecture was that you can basically imagine matrices through the combination of columns as well as through rows. Okay, so that was it for the today's lecture. Now one thing also that I wanted to note was that if you wanted to cover, now we have for the topics that we have covered, there are going to be some problem sets that you would get in the DeepML's platform. So you can head over there and solve interactive problems about matrix scalar multiplication in Python. So I will link down in the description and you can go there and solve the problem sets. Okay, that's about it for the today's lecture. Thank you.